Okay, chemistry time. Today we're talking about covalent bonding and acids. Covalent bonding, acids, and bases. I changed it a little even while I was standing here. Covalent bonding, acids, and bases. And the objective, it says, is model the formation of, that should say covalent bonds. I must have, oh, that's the objective from the lab. We did an ionic bonding lab, but now we're talking about covalent bonds. So let's put model the formation, and we'll do this one after the discussion, probably either Friday or Monday. Model the formation of covalent bonds. You already know what I'm going to ask you. What am I going to ask you, Gabe? Well, first of all, the question, what am I going to ask you, is what I was going to ask you. What am I going to ask you next?
What are covalent bonds?
Yeah, exactly right. Someone answer. What are covalent bonds? What is a covalent bond? Let's break it down a little. Let's break it down. I wish I hadn't done that. Let's break it down. What's a covalent bond mean? What's co mean? Thank you. What's co mean? Almost. Together. So co, it means co, together. Valent probably refers to valence electrons. Okay, now let's put them together. Yeah, they're okay. Covalent means that the valence electrons are together. Two or more atoms sharing valence electrons. Two or more atoms sharing valence electrons together. Valence electrons. Remind me, how are ionic bonds held together? What was the force of attraction between? Yeah, it was electromagnetic. It was the positive cation attracted the negative anion, and those two things were held together by electromagnetism. And I will tell you again, it is still the same force. It's just behaving in a different way. Well, it's behaving in the same way actually, but it's betwixt different particles this time. So whereas ionic bonds was the force of electromagnetic attraction between a cation that had lost electrons and an anion that had gained electrons, and that force of attraction held them together. Now it's the force of attraction between, for instance, if these are both oxygen atoms, it's the force of attraction between the electrons that normally spend time around this oxygen are also attracted to this oxygen. They're covalent. They're sharing them. Okay. A way we commonly express this, we don't normally express it like that, but a way we commonly express this is that we draw their electron dot diagrams. Tell me how many dots I should draw around oxygen to give it the right number of valence electrons. 6. 1, 2, 3, 4, 5, 6. Okay. What about for oxygen? How many valence electrons should I draw about? A 6. Yeah. 1, 2, 3, 4, 5, 6. Okay. Now, just looking at this, remind me, how many are they most stable with? 8. Is there a way that these two can share, covalent, to get 8 valence electrons? Sure. If this one shares that, and this one shares that, and that, we end up with a double bond, where now they're sharing all together between them 4 valence electrons. So this one has how many? 1, 2, 3, 4, 5, 6, 7, 8. 4 of which are shared. This one has how many? 8. 4 of which are shared. So they've bonded. And these, how many pairs of electrons? Electrons are always shared in pairs. So there's 2 pairs is a double bond. And a double bond is made of 1 sigma bond and 1 pi bond. You should have had those in your vocab. That's right, isn't it? You guys had sigma and pi bonds in your vocab. The sigma bond is, it doesn't really matter which one of these sharings is the sigma bond, but the sigma bond is the more basic. 1 sigma and 1, in this case, 1 pi. That makes a double bond. The sigma is the more basic bond. and then there can be pi bonds that are additional. Let me do another example. Let's do one this time with nitrogen. How many valence electrons should I have around this nitrogen to make this electron dot diagram? 5. 1, 2, 3, 4, 5. What about this nitrogen? 1, 2, 3, 4, 5. How many will they share? Can you tell just by looking at them? How many? Yeah, they'll have to share 3 between them, because that way they'll both have 8. They'll both act like they have 8. They'll both be more stable. 1, 2, 3. This one's going to share 1, 2, 3. They both have still 2 left over. What kind of bond do you think this is? Triple bond. This is a triple bond. So 3 pairs is a triple bond. And that would be a sigma and 2 pi's. These are Greek letters, and they just represent the I don't know, I guess the nature of the covalent bond. Let me read you what the book says. A sigma bond occurs when a pair of shared electrons is in an area centered between the 2 atoms. A pi bond forms when parallel orbits overlap and share electrons. So there's a physical difference between a sigma and a pi bond, but what you mostly need to know is that a sigma bond is present anytime there's a covalent bond. And then the more covalent bonds we say there are, we add pi bonds. So a single covalent bond is a sigma bond. A double is a sigma and a pi. A triple is a sigma and 2 pi's. There you go. I think you got it. It depends on how they share. That's how these covalent bonds are named. What do we call this now combined? Oh, and by the way, what force is this that I've drawn here that's holding them? It's still the electromagnetic force. It's not between a cation and an anion. It's between the electrons and the nuclei. So it's still the electromagnetic force. It's still the electromagnetic force. And what do we call this group now that we have these 2 atoms bonded together? Do you know? You should know. It's no longer oxygen atoms. It's now an O2, an oxygen molecule. These are called molecules. Molecules must be covalently bonded. And in fact, we sometimes call covalent bonds molecular bonds. This is the strongest bond in nature that I'm aware of. Thank you. No, specifically the nitrogen-nitrogen triple bond is the strongest bond in nature. It would take the highest energy to break. That's why a lot of times explosives, chemical explosives like TNT, the N in TNT is nitro. Nitroglycerin. This nitrogen bond is it's hard to break, and then when it does break, it's extremely energetic. It takes a lot of energy to form, takes a lot of energy, it releases a lot of energy when it breaks. So this triple bond is stronger than this double bond. Bond length, write this, bond length is inversely proportional to bond strength. The shorter the bonds are, the stronger they are. Analogy. Let me reach around in my brain for an analogy. Bond length is inversely proportional to bond strength. If, let's think of it kind of like lever arm. If I had 20-pound weight, 20 kilogram mass, maybe I should say, would this meter stick have an easier time supporting it on this 30 centimeter mark here or over here at the 90? The 30. It'd be the closer it is to where I'm supporting it, the closer it is to where it's pivoting, the less likelihood there is of breakage. I guess that's kind of a bad analogy maybe, but or think about a bridge made of Legos, or even a bridge made of wooden popsicle sticks in Mr. O's class. The longer it is, the more fragile it is. Yeah? It's the same with bond lengths. Bond length is inversely proportional to bond strength. The longer the bond length is, the weaker the bond is. Your book has a whole topic here that we're going to talk about, two things kind of briefly, and we're going to talk about them right now. The first is this idea of valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. We usually pronounce it VESPER, which is kind of a cool word. The valence shell electron pair repulsion theory it determines bond lengths and angles for a given bond. How many atoms are involved in a bond? 2, always 2. One bond is always bonding 2 atoms. There can be more than one bond in a molecule, but one bond is always bonding 2 atoms. And this valence shell electron pair repulsion theory determines bond lengths and angles for a given bond. And that's about all we're going to do with it at this time. When you're in college, or maybe if you're lucky and we get to it in Chem 2, we might talk about the specific shapes that are derived from these lengths and angles. But for now, it's good enough that you know just what the valence shell electron pair repulsion theory is and what it does. Another thing we're going to talk about is electronegativity. We talked about this a little bit last time, I believe. Electronegativity is the degree to which an atom, I was going to say wants or desires, but what's a better word for that, Lily? The degree to which an atom will obtain another electron. We talked about this when we talked about the periodic trends. But basically, the more electronegative an atom is, the more it wants, the more it would like, the more stable it would be with another electron. Maybe that's what I should have written. The more stable it will be. So which atom is probably going to be the most stable or have the highest electronegativity? Which will most like a new electron? We talked about this with, no, look.
Fluorine?
Fluorine. Yep, you got it. Fluorine is the most electronegative element. It wants another electron more than any other atom does. What's probably the least electronegative?
Francium?
It seems like it would be, but probably the noble gases. They kind of have electronegativity of 0. They don't want a new electron at all. But yeah, but by the trend, it would be francium. Because this one most wants to get rid of its electrons, right? And so the difference between these, difference in electronegativity between atoms in bond equals the bond nature, or we sometimes say the bond character, and to this tune. If the difference is greater than, let me erase some of this stuff down here. If the difference is greater than 1.7, it says it will be ionic. There's kind of a neat little table there, and I'll just rewrite the table. Difference in electronegativity. If it's greater than 1.7, the bond character just kind of means like how the bond is. The bond character will be ionic. If it's between 0.4 and 1.7, it'll be covalent, but probably what we call polar covalent. And if it's less than 0.4, if the difference is less than 0.4, it's nonpolar covalent. And you probably should remember what these two things mean from physical science, but I bet you don't. But first, let's do a little bit of math. So let's say, looking at our electronegativity chart, which I want you to look at with me on 265, look at page 265 for the electronegativity chart. Let's say that you both, look at page 265 for the electronegativity chart, please. You can share, but I do want everyone to look. Can I have a cup of tea, please? Look at page 265. let's say your boy, thank you. Let's say your boy oxygen is going to bond with magnesium. What's the difference there? Looking at that chart, they each have their own little electronegativity underneath them. What's the difference between the electronegativity value for oxygen and magnesium? Okay, so what's oxygen? No. It's 3.44. Magnesium is 1.31. What's the difference? 2.13. 2.13. It's the difference is 2.13. So where on this chart does that go?
2.13. It's above.
It's greater than 1.7. So what is the bond character for magnesium and oxygen? For the bond formed between magnesium and oxygen, it's ionic. And as Kendall correctly points out, one's a metal, and the other is a nonmetal. And a metal and a nonmetal generally, and this is where we get this idea, the rule of thumb that I have given you since you were little freshmen is that generally, and this comes from this table, got to get closer so you can see the numbers. Generally, a metal and a nonmetal will result in a number greater than this. The difference between those two will result in a number greater than this, and it will be ionic. What about, let's do sulfur and oxygen. Those two form a bond too. Sulfur and oxygen. Well, sulfur's is 2.58, oxygen's is 3.44. So what is that? 0.86. Where's 0.86 fall? Well, it's a polar covalent. Can you see of any that will be non-polar covalent? What about oxygen and oxygen? What's the difference in electronegativity from oxygen to oxygen? Zero. So this would be non-polar covalent. And what that means is that for this polar covalent one, the sulfur and the oxygen, this bond, the electrons like to hang out more with the oxygen. The oxygen is more electronegative. The oxygen wants the electrons more. So the electrons tend to hang out over here, giving it, we use this little lowercase Greek letter. Oh, that's not how it looks though. Partially negative, and this one therefore oh, heavens. This one therefore becomes partially positive. This is a polar bond. This little thing means partial negative, and this little thing means partial positive. Where do the electrons like to hang out more? With which of these do the electrons like to hang out more? Try again. Look at your chart. And how do you know? With which one do the electrons like to hang out more? Oxygen or sulfur? Remember, electronegativity is how bad they want an electron. No, try again. Oxygen. You got it. You got it. So they want to hang out more with the oxygen, and so that they do. They get a negative charge over here. This is really important, and you probably should write it down, even though no one maybe gave. Other than that, no one is writing down. This is really important because, in reality, it's not just a sulfur and a oxygen hanging out. It's a whole mess of them, and when this thing happens, now this unit, this sulfur and oxygen, because this end is negative and this end is positive, is attracted to the next unit's bottom, like the human centipede. It's always coming up in this class. Anyway, we'll cut that part. Bleep. Okay, but this end of this one is attracted electromagnetically to the next end of the next one, and they get a bond between them, an intermolecular bond. And that's where a lot of the properties we have of matter come from, are its intermolecular bonds. The properties of this T are largely because of the hydrogen bonds that exist because of the great polarity of water. Why would this be called polar? It has, say it, Lily, poles. It has poles like a magnet. And just like a magnet has poles, it can attract the other one's other end. I'm trying to think of a way that I can force you to write this down and understand it, but it's not coming to me, so please write this down and understand it. Okay, let's hear it, Willie.
I'll ask
Okay.
you. Really
Hey, I'm having a worry that you guys are not understanding polarity because it seems like you're not even trying. For instance, one of you's asleep.
2 poles.
So-
North pole, south pole.
Well, 2 poles, negative pole and positive pole. Why? Why does it? Hey, why does this have a negative pole?
Because oxygen has a greater electronegativity.
Yeah, oxygen has a greater electronegativity. Why does this one have a positive pole?
Because it has
Because
a
it's smaller.
Yeah, because the electrons want to hang out over here more. What about if we did the same thing for this one? The oxygen and the oxygen double bond. Where do they want to hang out with more? Neither. So this one is non-polar. That's why we call it non-polar. This one doesn't have poles. We're going to switch gears. This is how you do it. You put your foot on the clutch and you go. And since what we're driving is 18-wheeler, we switch it from like gear 36 to gear 37. Okay? And we're going to switch gears a little bit, and we're going to talk now about naming. I really hope that you review that segment of the video just now because I don't think you get this, and I hope you read your book and review this. Okay, let's hear it. Okay, yeah, and valence shell electron pair repulsion theory is
Okay, shell. What is the name again?
pair. We're gonna name these guys now. Covalent naming. Usually considered by most people a lot easier than ionic naming. We did ionic naming, but listen to me. Mark my words right here, Kindle Victory. Mark my words. You still have to know ionic naming. It is on the test too. But Mr. Cam, this is about covalent bonds. I don't care, Eric Cartman, whether it's about covalent or ionic bonds. You will have both covalent and ionic naming on your test. You will have polyatomic ions on your test. You will take a test over polyatomic ions. You have to know all of it. Covalent naming is what we're doing right now, though. Okay? The root or the most important fundamental part of this that we need to know is the number and its Greek prefix. I'm going to make you tell me these. 1. What's the Greek prefix for 1? Mono. 2. Di. 3. You need to write these down. 4.
Let me think. Tetra.
Tetra. 5.
Let me think.
Penta. 6. They're easy from here on out. Hexa. 7. Hepta.
Yeah, hepta.
8.
Octa.
Octa.
What?
9.
Deca.
Nona.
And
And 10.
Deca.
10 is deca. So basically we just use these with the number that are in it. So for instance, P2S5. Let's name it.
Diphosphorus.
Diphosphorus.
Sulfide.
Penta. Sulfide. We still change the name of the last one to end in "ide," but we just smoosh one of these prefixes onto the front of it.
Diarsenic.
Diarsenic.
Silicon. Solanite.
Silicide.
Silicide.
Diarsenic silicide. And on and on and on. What about this one?
What? BR3.
Okay.
And then FL2.
Nope, just F2. But that's, you got the actual thing we're doing right. You just didn't know the formula for fluorine.
I didn't know the abbreviation.
These should be pretty easy. We're going to leave it at that for these. You just need to practice. These should be pretty easy. But now we're going to move on to acid naming.
So acid naming.
Yeah. Let's real quick talk about acids and bases in general. First, there is a chapter that we do called acids and bases, but we don't usually do it till Chem 2. So acids, according to the most basic definition of acids, the Arrhenius definition of acids, acids release hydrogen ions in solution. And hydrogen ions are fairly reactive. That's why acids are considered dangerous and reactive, is because these hydrogen ions that they release are reactive. So the hydrogen ions that are released in solution will attack, so to speak, other stuff. Okay, would you please do something about this? Okay, Bases, according to that same definition, bases release hydroxide ions in solution. So let's give some examples. An example of an acid would be hydrochloric acid, HCl. You can see how this H might be released in solution. So if this is dissolved in water, the H is released and it reacts with other things, which is what an acid is. A base, KOH, you can see that this OH might be released in solution, which again is free now to react with other things. Bases are also very reactive. Some properties of acids: burn when they touch you. Right? Why would it feel like it's burning? What's actually happening? It's not fire.
The hydrogen's reacting.
Yeah, the hydrogen's reacting with you. Bases would probably feel like burning too because the hydroxide is burning. But bases also feel slippery. If you've ever gotten bleach on your fingers, it feels slippery. The bleach itself is not slippery. What's happening is
dissolving the top layer of your skin.
not even just dissolving, it's turning the fats that make up your cell membranes into soap. That's what bases. There's a process called saponification where bases reacting with fat produces soap. And so it makes the fats in your cells into soap. And so what you're really feeling is your own skin turned into soap, which is kind of sick. All mysterious questions that we never know how to answer when someone asks them
Because
weirdly
there's no
in class.
fat in your tube, your tube itself.
And also, why would you be... Nice, but not that bleach. Bleaching is a process. It was not household bleach. They were not like, here you go, bottoms up. Okay. Anyway, to name these things, bases are really easy. They're always just going to be, at least by this definition, they're always just going to be some metal hydroxide, magnesium hydroxide, copper hydroxide, calcium hydroxide. They're always going to be some of those. Those should be pretty easy. Those just follow normal ionic naming rules. So let me actually change my bracket to just be this. There are two kinds of acids that we worry about naming. There are binary acids and oxyacids. Binary acids, what's the word binary mean? Relating to two. Yeah. Binary acids only have hydrogen and some other element. Hydrogen plus some anion. And we usually name these as hydro something acid. Ic acid. So if it's HCl, as we already said, it's hydro I said if it's HCl, it's hydrochloric acid. Okay, what about HBr? Hydrobromic acid. Those are binary acids. So they're just hydro, the root of the anion, ic acid. Oxyacids are when they have oxygen. What's the only way that it could have an oxygen in it? If it was also a... Where are these things that have oxygen in it going to come from? Your list of polyatomic ions. You got it. Oxyacid come from the polyatomic ions.
It is hydrogen mixed with an oxyanion.
An oxyanion, like the polyatomic ion. So for instance, it would just be hydrogen plus a oxyanion. So it would, and it's always going to take the form of, if the oxyanion was ite, turns to us acid.
Wow.
8 turns to ic acid. So sulfite, so H2SO3. That's, you recognize SO3 as sulfite. Ite becomes us, so this is sulfurous acid. H2SO4, what's SO4? Sulfate. H becomes ic, so it's not sulfurous acid, it's sulfuric acid. Is that everything, Lily? That's everything.